In the vastness of the universe, two mysteries define the edges of our understanding. The cosmos itself, expanding, evolving, and giving rise to galaxies across unimaginable distances, and black holes, where matter collapses into shadow and the known laws of physics bend toward their breaking point. One reveals the origin and destiny of everything. The other reveals the limits of space, time, and even reality. To understand them together is to glimpse both the beginning and the end of the universe. Our journey begins at the very start, before the first star burned, before the first atom formed, before even space and time had settled into the rules we now know. The birth of the cosmos. The universe did not open with calm. It began in an instant of unimaginable intensity, an event not so much an explosion in space, but the sudden and overwhelming expansion of space itself. The distances between points grew, not because matter was moving through space, but because space was stretching between them. This initial expansion was so rapid that if you could have watched it unfold, you would have seen the universe double in size again and again in tiny fractions of a second. This era is known as inflation, a period when the cosmos expanded faster than light can travel. This did not violate the laws of physics, for nothing was moving through space faster than light. Rather, space itself was expanding. During inflation, tiny quantum fluctuations, minute ripples in the fabric of space-time, were stretched to cosmic scales. These ripples became the blueprint for all later structure. From them would grow the galaxies, stars, and planets that fill the universe today. In the smallest tremors of the earliest universe were the seeds of everything. Inflation ended almost as quickly as it began, but its echoes remain imprinted across the cosmos. The first light. Hundreds of thousands of years passed. The early universe was filled with a hot, glowing plasma. Electrons and protons, too energetic to bind together, light scattered at every turn. It was like trying to see through the center of a star. But eventually, the universe expanded and cooled. Atoms formed. Light, which had been trapped for eons, suddenly found itself free to travel. The fog of the early cosmos lifted. That first free light is the cosmic microwave background, a whisper from a time long before planets, long before galaxies, long before life. It paints a picture of the universe when it was only a few 100,000 years old. Across its faint glow, we can see tiny differences in temperature, tiny variations in density that trace back to those original quantum ripples. These tiny fluctuations are the fingerprints of creation. We study this ancient light with satellites and telescopes, decoding it like archaeologists reading inscriptions left by forgotten civilizations. It tells us that the early universe was remarkably uniform, yet not perfectly so. And it is those small imperfections that led to everything we now see. The cosmic web. As millions of years turned into billions, gravity began to shape the evolving universe. Invisible dark matter, which makes up far more mass than ordinary atoms, began to pull matter together. Dark matter does not shine, does not reflect, does not absorb light. Yet through gravity, it laid the foundation of cosmic structure. It formed a vast, interconnected scaffolding across the universe, a kind of cosmic skeleton. Along this skeleton, ordinary matter gathered. Gas flowed along the filaments of dark matter, forming knots where the threads crossed. These knots collapsed under gravity, and the first galaxies lit up the night. The universe became a web of filaments and clusters stretching across billions of light years. This cosmic web is the largest structure we know of, a sprawling universe-scale network shaped by gravity and time. Within this web, galaxies form families and communities. Clusters of galaxies gather into superclusters, linked by filaments that bridge unimaginable distances. In these places, stars are born, live out their lives, and die in brilliant explosions. From the darkness of deep time, the cosmos grew into a universe of extraordinary beauty and complexity, the expanding universe. A century ago, astronomers discovered something profound. The galaxies are not simply drifting through space. They are receding from one another. The farther away a galaxy is, the faster it appears to be moving. This is not due to motion through space, but the stretching of space itself. The universe is expanding. It has been expanding since its fiery beginning. Yet an even stranger discovery awaited us. Near the end of the 20th century, astronomers found that the expansion was not slowing down as expected. It was accelerating. Something, some unknown form of energy, was pushing the cosmos apart with greater and greater force. We call it dark energy, though the name hides our ignorance. It makes up nearly 70% of everything in the universe, yet we have only hints of what it might be. Dark energy governs the universe's future. If it remains constant, galaxies will drift apart until the night sky grows empty and silent. If it changes, the cosmos may face a different fate. It is the great unknown in modern cosmology. And so the universe expands, its galaxies like islands adrift on an ever-growing ocean. The death of stars. While cosmology tells the story of everything, another story unfolds within the cosmic web. A story of individual objects, of stars and their lives, their deaths, and their remnants. Some stars die peacefully, fading into white dwarfs, but the most massive stars meet a far more dramatic end. When such a star exhausts its nuclear fuel, it can no longer counteract the pressure of gravity. Its core collapses in milliseconds, compressing matter to extraordinary density. The collapse rebounds in a violent supernova, blasting its outer layers into space. What remains at the center is a neutron star, or if the collapse continues further, a black hole. Black holes are not merely objects. They are regions of space where gravity grows so strong that escape becomes impossible. Not for a spaceship, not for a photon, not even for time itself. The boundary of this region is called the event horizon, the point of no return. The event horizon is not a surface of matter. It is a boundary in space-time, marking the threshold between our universe and a region where our concepts of space and time break down. The event horizon. To fall toward a black hole is to witness the universe distort. Near the event horizon, gravity stretches time. For an outside observer, time appears to slow almost to a standstill. An object falling toward the horizon seems to move slower and slower, fading and dimming as it approaches the threshold but never quite crossing it. Yet for the object falling in, the journey is brief. The horizon is crossed without drama, but what lies beyond is unlike anything we can experience in the rest of the universe. Inside a non-rotating black hole, all paths lead to a central point where density becomes infinite, a singularity where the known laws of physics collapse. This is where our understanding ends. Rotating black holes, the kind that almost certainly exist in nature, have even stranger interiors, twisted by the swirling motion of space-time itself. The power of spin. Most black holes spin. They spin because the stars they came from spun. They spin because matter falling into them carries angular momentum. They spin because the universe itself has rotation woven into its fabric. A spinning black hole drags space-time around with it, a phenomenon known as frame dragging. In the region outside the event horizon, called the ergosphere, nothing can remain still. Space itself is moving. This rotation can power some of the brightest objects in the universe. When magnetic fields twist around a spinning black hole, they can tap into its rotational energy, launching jets of plasma at nearly the speed of light. These jets can span thousands of light years, shaping galaxies and lighting up the cosmos. Black holes, though silent and dark, can be engines of creation as well as destruction. The quantum black hole. For decades, black holes were thought to be perfect traps, objects from which nothing could escape. But the marriage of quantum mechanics and general relativity revealed a deeper truth. Black holes are not entirely black. Through a quantum process at the event horizon, they emit tiny amounts of radiation, now known as Hawking radiation. This radiation is incredibly faint for large black holes, far too faint to detect with current technology, but it has profound implications. It means black holes have a temperature, and because they radiate energy, they must, over unimaginable timescales, eventually evaporate. A black hole formed by a star will take far longer than the age of the universe to evaporate, but the principle remains. Black holes are not eternal. They fade. They die. And this raises a question so deep it reaches into the foundations of physics. The information paradox. If black holes evaporate, what happens to the information about everything that fell inside? Quantum mechanics insists that information cannot be destroyed. Yet general relativity seems to suggest that once something crosses the horizon, it is gone forever. This conflict is known as the black hole information paradox, one of the most profound puzzles in all of science. Does the information escape in the radiation? Is it encoded on the horizon itself? Does the interior hide a new layer of physics yet undiscovered? Solving this paradox may require a new theory, perhaps a quantum theory of gravity that unites the physics of the very small with the physics of the very large. Black holes challenge our understanding of reality at the deepest level, observing the invisible. For centuries, black holes were theoretical, predicted by mathematics, but invisible to observation. That changed in recent years. With the Event Horizon Telescope, we captured the first image of a black hole's shadow, a ring of blazing matter surrounding darkness deeper than night. We have detected the ripples of space-time created when black holes collide, sending gravitational waves rolling across the universe. These waves carry information from regions where gravity is at its strongest and most violent. Through these observations, we are witnessing black holes not as abstractions, but as real, dynamic, powerful objects shaping the cosmos. The cosmic connection. Cosmology and black holes might seem like opposite ends of the cosmic scale, one describing the entire universe, the other describing regions so small they collapse into themselves. But they are tied together through the same laws. Both rely on Einstein's theory of general relativity. Both test the limits of our understanding, and both hint at deeper truths. The early universe was once a kind of black hole in reverse, hot, dense, and extreme. The physics of the Big Bang and the physics of black hole interiors may be closer than we think. Some theories suggest that every black hole may give birth to a new universe. Others propose that our own universe might sit inside a larger structure, the product of a deeper layer of cosmological evolution. These ideas stretch the imagination, but so did the concept of black holes themselves, once dismissed as impossible. We have learned that the universe often exceeds our expectations. The future of the cosmos. As the universe expands faster and faster, galaxies will drift apart. Star formation will slow then cease. Over trillions of years, stars will fade, planets will freeze, and black holes will dominate the cosmic landscape. Even these giants will eventually evaporate, leaving behind only the faintest glow. The universe in the far future may become a dark, quiet place, but that is not the end of discovery. Because understanding the universe's fate helps us understand its beginning, and understanding its extremes helps us understand ourselves, creatures made of stardust, living in a universe of wonder. Closing. Cosmology reveals the birth and evolution of everything. Black holes reveal the limits of space and time. Together they form the boundary between what we know and what remains to be discovered. The cosmos expands. Black holes collapse. And somewhere between these two extremes lies the true nature of reality, waiting for us to uncover it. Our journey has taken us from the earliest instance of the universe to the darkest objects ever predicted. Yet in many ways, we have only just begun to explore the cosmic mysteries that surround us. For in every galaxy, every star, every shadow and beam of light, the universe continues to whisper its secrets, and we are still learning how to listen.